You know, usually when we talk about a commercial kitchen, there's this expectation of like relentless efficiency.
Right. It's supposed to be a total symphony.
Exactly. You have the prep stations, the sous chefs, the line cooks. They're all moving in this perfect harmony to get, 100 meals out the door.
Everything has its exact place.
Yeah, and you completely depend on that rigid structure to prevent total chaos when the dinner rush hits. But imagine stepping into this kitchen, and for every single dish on the menu, whether it's a really complex beef Wellington or just like a simple side salad, the chef has to stop, drop everything, walk out the back door, and make a completely separate trip to the grocery store.
Wow.
Just to buy ingredients they already have sitting right there in the pantry.
I mean, that sounds like a logistical nightmare that would bankrupt a restaurant in a week. The friction alone would just destroy any possibility of momentum.
It really would. And, well, welcome to this deep dive, where that specific brand of kitchen nightmare is exactly what we're going to explore today.
Only we aren't talking about culinary arts, right?
Right. We are talking about the invisible scaffolding that holds up almost every piece of software you use. Okay, let's unpack this. We have our hands on a really fascinating 2026 technical presentation by a developer named Lux036, and it's titled CMake Simplification, One Build File to Rule Them All.
That's quite the title.
Yeah, and whether you are a hardcore C++ developer fighting with compilers every single day, or you're just someone trying to optimize your own messy, complex workflows in life, this teardown is a total masterclass in eliminating technical debt.
It really is.
It starts as a story about aggressively cleaning up code, but it ultimately ends with a massive, completely unexpected unlock for AI-assisted coding.
You know, build systems like CMake are fascinating precisely because they are entirely invisible to the end user. They are essentially the underlying plumbing of the digital world.
The pipes behind the walls.
Exactly. But as we know, knowledge is most valuable when understood and applied. So we aren't just going to look at a list of things that were changed in this code base.
Right, we want the why.
Yes, we are going to examine the actual mechanics of those changes. We need to explore why structurally simplifying a foundation drastically improves the reliability of the whole house.
Yeah.
And why this specific methodology matters so much for the future of how software is written.
So let's start by looking at the old world, described in the presentation slides. The author literally calls it the multi-headed Hydra.
A very fitting name.
The core issue here was that this project didn't just have one front door for its build system. It had 7. There were 7 completely different nested CMakeList.txt files scattered all across various subprojects.
Which, this raises an important question. How does a system become that fractured in the first place?
Just over time, right?
Yeah, usually it accrues silently through good intentions. When you have 7 different entry points, every single subproject acts as if it is the absolute center of the universe.
Oh, I see.
Every time one of those subbuilds kicks off, it has to completely redeclare, refetch, and reconfigure the exact same dependencies from scratch.
So going back to our commercial kitchen, it's the chef walking to the grocery store 7 separate times to buy the exact same bag of flour.
Yes.
And worse, they had a little helper directory, a CMake folder, that essentially functioned as a junk drawer.
Every project has one of those.
Seriously. Over time, that directory filled up with absolute dead weight. The presentation notes it contained unused options for code sanitizers, obsolete to cache files, and amazingly, 3 completely different out-of-date copies of a package manager script called CPM.
3 copies.
3 of them.
Wow. And I bet most of those repositories never even invoked the sanitizers or the caching options anyway.
Nope, just totally dead code.
The real victim of this redundancy isn't just the human developer trying to navigate a messy folder structure, though. The ultimate price is paid by the continuous integration pipeline, or CI.
The automated checks.
Right, the automated cloud system that rigorously checks your code every time you make a change, ensuring it compiles and the tests pass before it goes live.
And the presentation calls this specific bottleneck the multi-directory dance. Because of this massively fragmented setup, the CI pipeline was forced to invoke CMake with a -s flag for every single subdirectory.
Ugh, the -s flag?
Yeah, it would run -s test, then stop, then -s standalone, then stop, over and over again.
Which is brutal because each of those -s invocations forces a completely separate CMake configure pass.
So it's literally starting over.
Exactly. You are essentially demanding that the computer forget everything it just learned about your system, your compiler, and your dependencies, and start completely from scratch 7 times in a row.
That is wild.
It turns a process that should be a really quick, unified structural check into an agonizingly slow, brittle, and sprawling mess.
Well, if you discover you have 7 kitchens poorly doing the work of one, you don't just reorganize the pantry,
Right.
You bring out a sledgehammer, you knock down the walls, and you remodel the entire building.
Rip it down to the studs.
Exactly. Which naturally pushes us into the one ring solution.
Yeah, the architectural shift here was total demolition. They ripped out those 7 fragmented entry points and replaced them with a single unified root CMake lists.txt file.
Everything was brought under one roof.
Everything.
And here's where it gets really interesting. Instead of having different files dictating different parts of the project, everything in this single new file becomes an option. You just run one unified command, CMake-B build.
Just the one command.
Yeah. And suddenly, simple Boolean flags act like master light switches for the entire project. If you pass in a flag like -d fractions _build _docs equals on, the documentation compiles.
And if you turn it off,
If you toggle it off, that entire component completely vanishes from the build scope.
that is so clean. And, the elegance really lies in what they were able to standardize across the entire project once that single root file was established.
Like what?
Well, they introduced a helper macro called target enable warnings. Because everything flowed through one single pipeline now, they could apply this helper to every single target. The libraries, the tests, the standalone executables, and the benchmarks.
Oh, wow.
Yeah, and it enforces a strict, unyielding rule. Compiler warnings are no longer just suggestions. They act as hard errors across all 3 major compilers.
So there is no more ignoring that little yellow squiggly line in your code editor.
Nope, you can't.
If there is a warning, the build just flat out breaks, forcing developers to maintain pristine code hygiene. But they didn't stop there. They also introduced a system-first dependencies pattern.
Right, the find package command.
Yeah, by combining find package with a CPM fallback, they built this highly intelligent decision tree. The presentation lists packages like FMT, speedlog, docdist, rapidcheck, and xoctave.
And the mechanism behind this is brilliant for local development.
How so?
Well, if you are a developer working on macOS or Ubuntu, and you already have those specific packages installed on your local machine, the build system detects them and uses them instantly.
Oh, so it skips the download.
Exactly. It skips the expensive process of fetching them from the internet entirely. And if you don't have them installed, the system just seamlessly falls back to fetching them via CPM, completely identical to the old method.
So there's zero risk, but a massive potential upside for speed.
Exactly.
But my absolute favorite part of this whole one ring remodel is their export strategy. They kept it minimal, exporting exactly what consumers need and absolutely nothing more.
A very smart move.
But to prove it actually works, they built a consumer project called Test Installed. I'm guessing that historically, if you only test your code in the build tree where all your messy intermediate working files are sitting around, you're essentially testing in a contaminated environment, right?
Yeah, absolutely are.
The code might only work because it's accidentally leaning on some temporary file that simply won't exist for the final user.
That is the exact blind spot the test installed consumer addresses. Testing in the build tree is intuitively what most developers do, but it is dangerous.
Because it's a false positive.
Right. The person downloading your software doesn't get your messy workbench. They only get the final installed artifacts.
Yeah.
If you forget to include a critical header file in your install instructions, your local build tree tests will still pass because that header is sitting right there on your hard drive. But the moment a downstream user tries to build your package, it will completely crash.
Because they only have what you officially handed them.
Exactly. So the test installed consumer forces the system to run the CMake install command, takes those final packaged artifacts, and then attempts to build a tiny, completely isolated project using only what was officially installed.
It verifies the reality of what you were shipping.
Yes, acting as a definitive safety net.
So, okay, the blueprint for this new architecture looks bulletproof on a slide, but pouring the concrete is always a different story, right?
Always.
The real trial by fire is what happens when this single file solution is actually forced to compile real, sprawling C++ code. And we have 2 specific case studies here, Alago Kaipi and fractions-CP.
And the transition from theory to reality was immediately rocky.
I bet.
In AlgoStep, they rolled out this unified build system, and the CI pipelines instantly failed on both Ubuntu and macOS.
Ouch.
Yeah, the presentation refers to this as invisible runtime chaos. There were no helpful compiler warnings pointing to a syntax error. Instead, there were spontaneous runtime exceptions blowing up the code during execution.
Wait, so if the syntax was totally fine, but the program kept detonating at runtime, I'd assume the underlying components were just fundamentally misaligned behind the scenes, like the left hand suddenly didn't know what the right hand was doing.
That is exactly the mechanism of the failure. It all traced back to a missing macro called spdlog compiled lib.
Okay, what does that do?
Well, when they simplified the build down to one file, they accidentally caused a divergence in how the code talked to its logging library, cvdaylog. To understand why this causes an exception, imagine a construction crew building a house.
Okay.
Half the crew is reading the blueprints in inches, and the other half is reading them in centimeters.
Because someone forgot to hand out the master translation sheet.
Exactly.
So the house looks fine on paper, but the moment you try to put the roof on, nothing aligns and the whole structure collapses.
Perfect analogy. By missing that specific macro, the project had header-only definitions completely clashing with compiled registries. The C++ components were speaking two different dialects, resulting in a duplicate logger exception that completely destroyed the macOS build.
Oh, man.
And they also discovered that their code coverage tool, gcover, was abruptly crashing.
Why was that?
The coverage options were being applied blindly across the board, even on the MSVC compiler on Windows, which natively skips those specific Unix-style coverage flags. They had to manually platform guard the tool so it only ran on GCC and Clang compilers.
Okay, I have to push back here, though. We just spent 10 minutes talking about how elegant and frictionless this new single-file system is. But hunting down silent macro divergences that cause obscure duplicate logger exceptions, or figuring out platform-specific coverage tool crashes, that does not sound simple.
It doesn't.
Deleting the old code was the easy part. Surviving the fallout sounds like a massive headache.
The fallout was severe, but we have to look at the philosophy of why it happened. This struggle perfectly validates what the author calls the golden rule of build systems. One configure, one build, one test command. Everywhere.
Right.
When you rely on a sprawling, seven-headed build system, catastrophic bugs like that macro divergence can easily hide inside the complexity. The old messy system wasn't working better. It was actively masking fundamental architectural flaws in the code.
So the new system didn't cause the bugs. The new system just turned all the lights on in the kitchen and showed you exactly where the cockroaches were hiding.
Yes. By forcing every single component through one strict unified pipeline, they flushed out the hidden rot. Once they added the missing macro back in and platform guarded the coverage tool, a single commit turned both failing platforms green. The pattern proved its worth.
Which brings us to the second case study, fractions.NA. This project was the Great Purge. They applied the new pattern and just aggressively went to town.
They really did.
They deleted 568 lines of CMake code scattered across 7 obsolete files. Test entries, CLI entries, doc entries, the aggregator, the entire examples directory, including that third redundant copy of CPM we talked about, all of it was completely wiped out.
It's so satisfying to hear. They replaced all 568 of those fragmented lines with a single, highly readable 217-line file.
Wow.
It was a net reduction of over 300 lines of code while simultaneously increasing the functionality of the system. They unified their CI down to just 5 clean workflows: Ubuntu, install Windows, macOS, and documentation.
But even this purge, they hit a trap during local verification on Windows, right? Something regarding the MSVC generator.
Ah, yes. Windows compilers can generate multiple configurations, like debug and release, concurrently. The developer discovered that when executing the install command on Windows, they had to explicitly pass the flag --config debug.
And if they didn't?
If they omitted that flag, the multi-config MSVC generator defaulted to release mode. That mismatch broke the lookup for the stdlog dependency because the system was searching for the release version of the library while the project was trying to build and debug.
Classic Windows headache.
Nah.
But once they explicitly declared that configuration, they pushed the 7 semantic commits, and all 4 push-triggered CI workflows went completely green on the very first run.
A huge win.
Fixing your own house is deeply satisfying. But in the world of open source software, your code base is often the load-bearing wall for someone else's project.
Absolutely.
If I am a downstream user and I see you just ripped out 600 lines of your internal build system, My immediate fear is that I'm going to have to rewrite my own code just to keep the water running.
Which is a totally valid fear. But if we connect this to the bigger picture, this is the ultimate test of API stability. The presentation details how this internal demolition affected two sibling repositories, RatTrig CP and ProdGM CP, which actively consume fractions TP by pinning a specific CPM tag.
And the critical distinction the slides make here is that the build graph completely changed, but the API interface was fully preserved.
Think of it like a massive plumbing renovation in a city. You can rip up the streets and completely replace the main water lines with a radically different design.
Yeah.
But as long as the water pressure is the same and the faucet on the resident sink turns on the exact same way, the homeowner doesn't even need to know the renovation happened.
Right.
The presentation proved this by diffing the header files. They were byte identical. The target name that downstream consumers call fractions colon fractions remained completely unchanged.
But wait. Because the new single root file builds everything by default now, including the test suites, wouldn't downstream consumers suddenly inherit all those extra testing dependencies if they just pulled the library in normally?
They would, which is why downstream consumers had to utilize a consumer opt-out.
How does that work?
Because CPM is highly intelligent and deduplicates shared dependencies by name, the consumer simply instructed CPM to skip fetching the fractions test suite entirely.
Oh, that's clever.
Yeah, that opt-out bypassed any potential target conflicts, keeping the downstream build incredibly lightweight.
I did see one slide mentioning a specific 0xC0000135 error in ProdGM CP during this phase. At first glance, that looks like a massive regression caused by ripping out those 600 lines. I'd assume the new CMake system failed to link a critical library.
It absolutely looks like a build system regression on the surface, but distinguishing between a true CMake failure and a local environment configuration error is crucial here.
Okay, so it wasn't CMake.
No, that error was a pre-existing gotcha totally unrelated to the CMake simplification. The ProdGM CPUT project was pulling shared dynamic libraries for FMT and speedlog from a Conda environment.
Oh, Conda.
Yeah. To find those DLLs at runtime, Conda's library bin folder physically has to be added to the Windows system path. Once the developer accounted for that environment variable, they ran the tests, and they achieved the holy grail, 0 regressions.
Incredible. So we have faster CI pipelines, happier human developers, and 0 downstream regressions. But, the presentation flips the script at the very end.
The plot twist.
Yeah. The ultimate beneficiary of all this rigorous structuring isn't human at all. What does a single-file CMake architecture mean for AI coding agents?
This is where the presentation elevates from a standard refactoring post-mortem into a legitimate glimpse of the future. AI coding agents care deeply about build system simplification because they operate under severe mechanical constraints.
Okay.
They are entirely pattern-driven and context-limited.
So what does this all mean for how an AI actually processes a code base? If I think about an AI, I think of a brilliant chef who unfortunately has a very strict short-term memory limit.
That's a great way to put it.
They can only hold, say, 50 ingredients or instructions in their head at any one time. If your project's build instructions are scattered across 15 different recipe cards hidden in different drawers, the chef wastes their entire memory capacity just trying to figure out where the kitchen tools are, leaving absolutely no mental room to actually cook the meal.
That memory limit is exactly what we call a context window, and it is measured in tokens. Every file an AI opens and every line of code it ingests costs precious tokens.
Tokens aren't cheap?
No, they aren't. By condensing a 15-file build system into a single root file, you are radically saving tokens. The presentation outlines 7 specific ways the simplification acts as a massive unlock. You provide less context to load, for one.
Right.
You create a single source of truth. Dependencies are declared exactly once, so the AI doesn't hallucinate over a stray configuration buried in some subfolder.
And the uniform commands are a total game changer. Because CMake-B build now works universally across every repository, the AI doesn't have to burn tokens guessing or learning a bespoke build command for every individual sub-project.
Exactly. You also provide explicit intent. An option like if build tests is mathematically logical for an AI to parse.
It's just a Boolean.
Right. It can perfectly predict the cause and effect of toggling that Boolean switch, whereas relying on an ambiguously named directory like tests requires the AI to infer human intent, which often fails.
And that test-installed consumer we discussed earlier gives the AI a deterministic safety net. It provides a definitive green or red verdict, so the agent explicitly knows if the code it just generated actually resulted in a working, installable package.
What's fascinating here is how the author frames the danger of the old system. They call it silent sloppiness.
Silent slop.
Yes. AI agents fundamentally learn by iterating. They attempt a code fix, they build the project, and they check the result. If your build system allows silent failures like missing a logging macro but compiling anyway, or generating hundreds of compiler warnings that don't actually stop the build in them, an AI will simply hallucinate a fix that isn't real.
Because the system didn't stop it.
Exactly.
Because the computer never explicitly told the AI, hey, this is broken. It just quietly let the sloppy code slide through.
By utilizing that target enable warnings helper to turn compiler warnings into hard errors, the new system creates an instant, undeniable, machine-readable feedback loop. It removes all ambiguity.
So the AI learns faster.
The AI knows immediately if it made a mistake, making autonomous verification cheap and incredibly fast. And what's really cool is because this single file pattern is uniform, once an AI agent successfully learns how to navigate one repository, that structural expertise is immediately and perfectly transferable to all the sibling repositories.
Wow. You know, I am realizing that simplifying this build wasn't just about cleaning up technical debt for the sake of the human developer's sanity.
No, it wasn't.
It was literally about formatting the code base so a machine could effortlessly read, navigate, and modify it. We went from 7 messy, redundant entry points to 1 elegant file. We crushed the CI pipeline times, deleted hundreds of lines of obsolete code, and in the process, accidentally created the perfect frictionless environment for AI coding agents to thrive.
It completely reframes how we view project architecture. We are no longer just writing code for each other.
We really aren't. And for you listening, even if you don't write C++N, even if the word CMake makes your eyes glaze over, the underlying principle holds absolutely true for whatever field you operate in.
Absolutely.
The best system is the one you don't have to think about. Whether you're organizing a commercial kitchen, structuring a corporate team's workflow, or writing software, structural clarity and a single source of truth will always win.
Which leaves us with a rather profound question to consider.
Let's hear it.
For the last 50 years, we have explicitly designed our programming environments, our languages, and our project structures to be readable by human eyes. We prioritized human logic.
Right.
But as AI rapidly becomes our primary co-pilot, writing and reviewing the bulk of our code, are we going to have to rethink this entire paradigm? Are we on the verge of having to redesign not just our build systems, but our entire programming languages to be token efficient and instantly machine readable rather than human readable?
It makes you wonder. If your kitchen was suddenly staffed entirely by highly efficient robots with limited short-term memory, would you still organize your pantry the exact same way you do today? Look at your own daily workflows. What complex, sprawling processes are you holding on to that were built for an era we've already left behind? Something to chew on. Until next time.